Last year too, so it's okay. All right, you're tuning in late, everybody. Everyone want to say hi? Hi. There we go. We're good. It's on the paper. Just read. Okay. So I'd like you to think about this vector in particular, this matrix in particular, as a transformation, clearly, of two-dimensional vectors. This is something you could multiply two-dimensional vectors by, and what would you get? You'd get more two-dimensional vectors. And in particular, think about what this is doing to vectors in general. So take a couple vectors, your favorite vectors, two-dimensional vectors, and multiply this by them, and see if you can't figure out what geometrically this is doing. Go ahead. And then when you're done, it won't take you long. It'll only take you one or two multiplications to realize what's happening. See if you can somehow prove what you think is happening. Prove it.
Oh, yeah, it's -1. So these might be negative like that.
Yeah, multiply by whatever vectors you like. Try a few. Try the vector 5, 7. Or the vector -23, 15.
Oh, wait. Are you saying like -23, 5, oh wait, that's not.
Whatever, I spent two, the vector that has two
-5. Yeah, it's gotta
What if I do like 1? What if I do things
row.
that you're
You can do whatever you want.
buddy?
Did you figure out what it does yet?
No.
Tell your neighbors once you figure out what you think it's doing. And also, like I said, rise to the level of some sort of proof. The proof here doesn't demand too much of you. Right? But see if you justify that it's not just a coincidence.
Oh, yeah, you're right. Oh, these are like vector translation.
That's why I'm doing the thing. Okay, this is the y-axis. If your x point is positive, in order for it to get negative, you have to over the y-axis, not the x.
All right. How are we doing?
Love you, Elizabeth.
All right. What did you guys say in the back, Sam? Did you guys come up with a geometric description of what this is doing? What did you? How many people said that?
I knew it.
Yeah, I think that's a good way to say it. And how might we prove that in some sense? I don't know. There's not much to do here. I just will justify it in a general way. How would you do that? Yeah, go ahead.
Multiply by x, y.
Yeah, multiply by like your two favorite letters, right? And see that what do you get, of course?
Peanut butter.
What?
That's peanut butter.
You see that the y-coordinate, whatever you chose, the y-coordinate won't change and the x-coordinate will be the opposite. Okay, so I think we've justified this.
Oh, wait. Can't you just like...
All right, so if that was fun, and I think it was, then now try to do the same exercise with these, just for fun, okay? So come up with a geometric description of each of these matrices, and already be thinking about the fact that you're thinking about square matrices in a very new light than you ever thought about them before. They're verbs now, you guys. They're not nouns. Catch that? They do stuff. They don't are things. They do things, right?
Oh.
These are actions. These matrices do things.
Yeah, they call themselves in brackets and then they don't associate with the outside world. So the first one is the same thing.
The first one, XY. Just one.
Okay. You have negative x. So the third one is a horizontal stretch, but back in 3, right? Vertical stretch? Yeah, it's a horizontal stretch with
One day I'm going to figure out how to do all of them.
Oh, this one's V and
No, it's a vertical stretch if it's 3x. Plan. No, wait, it is a horizontal stretch. I don't get it. I give up. I'd just like to personally address me from the future retaking this class and listening to this recording.
Congratulations, you're multiplying everyone.
Everybody just missed my golden joke. That was
Yeah, but
definitely
it's not
missed.
anything like that. Yeah, because X
What is
back
B?
Y. Wait, is this a stretch or a stretch? It's a stretch. X is
But think about what it does to vectors. I mean, if you have the vector x, y, and it's matched to the vector 3x, what does it do? All right, let's go through these here. So, what does the first matrix do? Anyone?
Standard form identity.
Well, geometrically, what does it do to vectors when you multiply them?
Nothing.
Nothing. Yeah, nothing. Right. Let's skip B for now. What about C? What does that one do? How about Anya? What'd you say
Please
there?
don't call me. I don't know any of them.
I think you're absolutely right. Can you put a finer point on it? Which way? By how much? Like all that. Multiply this by xy is what a lot of people I saw doing. Or by your favorite point. What does it do to that point? We'll come back to you in a second. What about D? Dina? What do you think? Did you come up with... Uh-oh, sorry. All right, we'll come back to you in a second, too.
No, but like when I multiplied it by xy, I got y and then y.
Y and then Y?
Yeah.
Oh, that's weird. So X got eliminated?
Yeah.
Oh, weird.
Oh my god, it's a straight line.
Do you, Anya?
Wait, is that Y over X? It's Y X.
Anya, you want to take C?
It's an inverse.
Okay, yeah. Can you give an idea why that's true? Or why would it be a horizontal stretch? Right, yeah. So in the y coordinate, nothing happens. Yeah. Dilation or stretch or something, however you want to say it. By a factor of 3. And then D, Dina, did you want to say something more about that? Oh, okay. Okay. And do you have any geometry to talk about there? What's going on there? If we exchange the x and y coordinates of a point.
It might be the inverse, so like reflected across y equals x.
Yeah, it's a reflection over the line y equals x is I think an okay way to say it.
Yes, Katie, it is. Good job.
All right, and then this one's a little weird. Sorry, I made that B. I should have made that part B maybe, but anyone have an idea as for how that looks or what you want to say about it? That's a little weird. What do you think, Stephanie? B units? What's BB? Okay, so whatever the y coordinate was, it moves it that many to the right. That's certainly correct. That's not, does it correspond to a translation or a rotation or a reflection of some kind, some rigid motion or anything? Or no, not really. Yeah, the name of this is a shear. And maybe you're not familiar with this transformation, but here's...
No, because like it doesn't lie units to the right. So it's not like it's not the number of units to the right. It's not always the same.
Yeah, it turns things into kind of parallelograms, right, like that.
Well, that is
Like that.
Wait, so what does it do to a line?
So notice that if anyone worked it out, you get the y coordinate remains the same, doesn't it? Yeah. So you can see that all the points, what do they do? Well, all the y coordinates of points stay the same, but the x coordinate moves by a distance of y depending where you are. So it kind of it's called a shear. That's called a shear transformation. I don't know. There you go. It's not super important you know that. It's just like I just thought I'd show you one that's not one of the other ones. It's just show you what else you can do. All right, let's try and kind of do the reverse question. Can you come up with some matrices that do these things? If you haven't already started trying, try. Yeah, Brandon?
Not sure I know how to do it. It takes all my willpower just to not give up on letter A.
Really moving at y units to the right.
Bad mood today. Because I've honestly spent a difficult squad. I think I'm gonna play.
Is this negative 1, 1, 0, negative 1?
Like, oh, I tried to study it, but I didn't get it.
It was completion points. Is this the answer about the numero? No.
Wait, is a reflection over the x-axis equal to -1? Yeah, so we're gonna have to have a frequency of negative xy, right?
What?
There's something like talking husky.
What?
The husky that talks. It's not a cat. Okay, how do you do a rotation on a matrix? I've given up on A.
Sorry, that one took me like so long to figure out.
Where? Oh! So then the bottom one is negative 1, right? 1, 0, 0, negative 1. Yeah, like so. I am brilliant. Take that.
Oh, no. I lied. Don't you do it?
All right. Do we have any of these yet out there? What's the x-axis? The reflection over the x-axis one.
1, 0, 0, negative 1.
Good. Anyone? This is interesting. A rotation by 180 degrees.
Wait, just give me 1 second.
What do you need? Does that work? Someone else check this on us. Let's try that. So is that like a reflection over the x and the y-axis?
Yes.
That's the same.
Oh,
Is
yeah!
that the same thing as rotating something by 180 degrees?
Good job, Pink.
Okay. All right. I guess it is. Okay. Dilation by a factor of 2 in all directions. Yeah. So far, so good. What about? Ooh, interesting. Rotation by 90. You think you got it? I think that's fine. It didn't specify. It's not your fault. It's my fault. Okay.
I don't know if this is right. 0, -1, and then 1, 0.
Let's write it down and then think about it. Okay.
Oh, 0, 1.
This should be a 1 here.
Well, I didn't write by accident.
All right. So wait. Let's think about it here. Does that work? I mean, think about where that sends x, y, for example, or something. Sounds like that sends a point x, y to a point. Does that make sense? That you get negative y, x? Keep in mind that it's a rotation. I think I like it. I think it works. Where does it send? Where does it send the vector I? Where does it send the vector j?
In a certain direction.
I want you to think about where I and j go in particular. Do they go in the right place if it's a rotation by 90? Okay.
Oh, we need a vector.
Yeah.
But they move? I thought they're
Anyone
all
come up with
0,
E
0,
yet?
1, 1. Nina's so smart. She's so good.
Anyone come up with E? Let me ask you this: on all the other ones you see on this page, where do all of these map the vector 0, 0? To 0, 0. In fact, in general, the matrix A, B, C, D maps 0, 0 to 0, 0. In fact, there's no other way around it. But a translation right to would map 0, 0 to 2, 0.
Also, it's impossible.
It's not possible. Not by multiplying the matrix. So the trick question there. So it turns out that as simple as that might sound, it's not a linear transformation. I just wanted to make sure you're clear that you, after doing all these, you're like, wow, I can do anything. Well, not quite. Not quite. Okay.
That's a lot. Wait, what is D?
I'm gonna. It's not possible. E is not possible. All right, let me try one of these on for size. We got a house coming up here. Let's see. There we go. Okay. Square. All right, here we go. Let's do. So here, right now, we've got the identity applied to this. Can you guys see this? Okay. It's so exciting. Okay. So what would we like to do? What would you like to do to the square, friends?
Make it rotate.
Rotate 90 degrees, which is what we were just talking about. So 0, 1, -1, 0.
Is this a shear?
Did that rotate it? Yeah, we should see a shear too. What would we say? 1,
1, 1, 0, 1.
would be an example of a shear, right? Let's do something simple. Let's do just a reflection over the y-axis and over the x-axis simultaneously. There's our rotation.
It's going like what?
It would be more fun to do all of this with a house, don't you think? Okay.
Wow, that got so fun.
Me too.
Did you say that got so fun so quick? Let's shear the house too, actually.
Oh my god, you sheared a house.
Let's
Is that why those tools are called
Let's
shears?
stretch-
Because they do that?
let's stretch it 3 times horizontally. Let's stretch it both
Wait,
directions.
are you house shaving?
It's
Yes.
long.
I'll have you know that big long house is super, super modern and expensive.
Are we having fun yet? Okay. All right. Does yours? So now I want to at least, we won't say too much, guys. We won't say too much about 3-dimensional transformations. Yours is a little different on there. Sorry, can you change that last one to a -1 there? Okay. All right. Now, and with this matrix in mind, thanks, guys. Can you think with me about what this matrix does? What did I do with my pen? Let me see.
Hi, Kevin. Didn't even say
Yes.
I said change the one on your paper.
until just now.
Elizabeth's gonna find it for me. I can already tell. She's gonna find it.
But it's okay, Kevin.
Wait,
We'll
did
be fast
you lose
friends.
your pen?
I got it. I found it. She would not have found it. All right. So let's think hard about what happens to this here. So one lens I should tell you again. Let's go back just for a second to these. The lens that maybe you want to have as well is not just like where does x, y go, but where do I and j go, right? So on these, let's pick this one. Where does I go under this transformation? That is the vector 1, 0. Where does it go?
On and on and on.
It goes to 3, 0. Where does the vector j go?
0.
Where does, for this one, yeah, 0, 0, 1. Where does I go under this one? Where does I go? That is 1, 0. If you multiply this by 1, 0, what do you get? Still 1, 0. Where does j go? That is 0, 1. Where does that go? 1, 1. Yes? So, do you see those answers actually immediately before you, before we even have to... Where does I go? 1, 0. Where does j go?
1, 1.
1, 1. Do you see them right before your very eyes?
Remember when you did super fast as the summer?
Where do you want... Let's do the rotation by 90. Where do you want I to go for the rotation by 90? You want it to go not 1, 0 anymore, but to 0, 1. And where do you... And then you want j, 0, 1, to go to -1, 0. Do you see I and j and where they go now? This is where I goes. And this is where j goes. Yeah? On all of these, the first column is i's destination, and the second column is j's destination, right?
Oh, I get it now.
Keeping that in mind here,
Technically.
let's think about this guy now too. Where would I, j, and k go? Well, let's think of the x-axis here and the y-axis here and the z-axis through my head. Again, x, y, z, okay? So what happens to the I vector in the x direction?
It goes like this.
What happens to the I vector? Yeah, if you multiply by 1, 0, 0, you just get 1, 0, 0. Yeah, it doesn't go anywhere. I doesn't go anywhere. Where does j go? It gets mapped along the what? Z-axis. So the positive, a vector in the direction of the positive y-axis gets mapped to a vector in the positive z-axis direction. And where does the z vector go, the k vector go? It gets mapped along the negative y-axis. So what is happening here geometrically?
You got reflected over the XE.
Well, remember, this one stays the same, doesn't move at all. This one goes to here, and my head goes to here. Do you see what's happening? This is staying fixed. This is moving to here, this is moving to there.
It's a reflection across the.
It's not a reflection.
Rotation.
Rotation.
It's a rotation by 90 degrees around the x-axis, right?
I don't get it.
So that's the last time we'll discuss this in 3 dimensions. I just wanted you to understand that this discussion does
Good, it won't be on the
go into
test.
3 dimensions too, right? I, J, we can actually track where I, J, and K go in those 3 columns. So let's also now think about this vector. We've been giving you matrices that are like a little bit weird, right, so far. But this one's really weird, right? It's hard to track if I ask you what is happening here. And the answer would, of course, be, well, there's like a reflection and a shear and a rotation, or, some weird stuff happening, right? But is it okay does this send vectors to other vectors? Yeah, it's still some kind of linear transformation. And one way that maybe we can track the linear transformation, even if we can't fully describe it geometrically, is by thinking about where I and j go. So if you've been hearing me on this last conversation, where does I and j go? Where does the point 1, 0 go? Yeah, 109, 1 is where you can try the multiplication yourself, and you'll see, of course, that you just get 109 and 1. Where does 0, 1 go? K, or j, sorry. What does it go to? 3, negative 2. Where does 0, 0 go? Every linear transformation has that as the answer to that one. And what about 1, 1? That is actually somewhat interesting.
109. Wait. 109.
Yeah, 112. 112 and negative 1, right? So this is easy and it's not worth mentioning. These two are easy because you can just look at them, and this one is the sum of the 2 rows, right? To get those coordinates. So in general, you could say that about any linear transformation, and any linear transformation, A, B, C, D. I've written them in columns here. That this is actually a really helpful way to see it. And actually, in the first applet I showed you, the thing we were playing around with was the unit square. Did you see that the very first before the house? And that's this unit square is the thing that has these as the 4 coordinates, right? 0, 0, 1, 0, 0, 1, and 1, 1. Okay. And so we can track based on thinking about where these 4 points go. Really, we can get a good handle on any linear transformation. So this one in particular gets, if you're mapping, I'm using this matrix A, B, C, D. It's in your notes there, but I just want to show you. They're like, here's the unit square, 0, 0, 1, 0, 1, 1, 0, 1. And under this mapping, assuming that these letters are used, where does 1, 0 go? AD. Yeah? Where does 0, 1 go? CD, right here. And where does this point, 1, 1 go? Well, it goes to A plus B, comma, A plus C, comma, B plus D, right? And you can actually see, and of course 0, 0 stays where it is. So this is like the pre-image, the square, the unit square, and the parallelogram here is, after that transformation, is the image. Okay. Now, the only other thing I'd like to have us think about is the area of this parallelogram. And I promise this is a really fruitful thing to think about. Now, I'm going to, just for the sake of time too here, I'm going to give you this picture to start with, and I'd like to see if you can come up with the area of the parallelogram with the help of this picture. Do you agree with all these coordinates? If this is the point AB, friends, isn't this side length of this triangle A?
Yes.
And furthermore, if this is the coordinate a plus c, well then this must be c more than that. So this little side length of this rectangle down here is c. Apply that kind of logic to everywhere else in this diagram, and spend a minute at your table see if you can come up with a really tiny expression for the area of the parallelogram. Use some geometry to try and get you there. Okay? Triangles, rectangles,
Isn't the height,
maybe use some subtraction.
the height e minus b? Isn't the height b minus b?
The area
So if you make a line,
It's the root of b squared plus b squared plus c squared plus d squared, right? What's normal? That's not like this. That's not like this. Okay, so, right?
Did you already find some things that have the same area in this picture? Like this rectangle
and that right too.
and this rectangle are both b by c, right?
oh, we need to find the area of oh. And all the other triangles are the same size.
But not all the other triangles are the
really?
same size,
Uh,
I think.
now. Oh, wait.
Right, but this one, this is a by b, and this one's a by b, so I agree with that.
And then that one is D by
Oh, yeah.
C.
So you find the area of b by c.
What's the area of the whole rectangle?
And then
Can
you
you come
subtract.
up with a binomial?
That is crazy. Mr.
Multiplication
Mason,
problem?
So intelligent.
But actually, like it says, please do what it says. Simplify your expression.
Okay.
Yeah, multiply it all out.
Okay, so we have to multiply it all out.
Yeah, I mean, so
Simplify.
simplify it as much as possible. There's all sorts of stuff that's going to cancel out and combine.
I don't get it unless
It's worth it, I promise.
D plus c. D plus e times a plus c. Okay. Can you say that to me? Because I was copying the
Yeah, for those who are like, I don't know what to do, I think most of us are taking the area of the entire rectangle and subtracting all the areas of the things we don't like to get the area of the parallelogram. I think that's what everyone's doing.
Good job, team.
alright, team. Only simple is good.
Okay, so this is the entire one, and you have to subtract
Right, 2c.
times c.
Wait, is c equals to b? Oh, yeah.
Oh, this is gonna be difficult.
The big triangle?
Oh,
Wait,
okay.
hold up. I had an addition.
I just not been doing.
Come on, guys, you're good at singing. This is the final page.
It's a big moment.
Yeah. Okay, well, I want to use the final page.
So the size are, you take the a plus c, use it times.
This is a lot of writing. Yeah, that's fine.
All right, a number of you are getting it. For those who are starting the process, is this, just so you're not on the wrong page here, are you doing something like this?
Yeah,
Right, area of the rectangle was this,
but not really.
and then you're subtracting, this is there are two copies of the same triangles like some of you already made note of. And there's two copies of that rectangle BC in the two corners, so I'm just subtracting two copies of all these things off. And after lots of simplification, some of you have already seen, good job, what do you get? Yeah, the determinant of the matrix. Now, we've been using determinants recently here for a couple things, including all the way back to the cross product. But it hasn't come out, and this, I think this is a big important idea, is that the area of the parallelogram is the determinant. This is the big idea here. It's a big idea, it's an important one. I don't think it's just kind of a cute little add-on. I think there's an important thing to say about some of the transformations we've talked about. Let me end by asking a few mind-blowing questions to you, okay? How do you do a reflection and a dilation?
Put a negative thing to
Yeah, maybe you add like a negative, you have like 2's and a negative, you make a -2 or something, okay. But, so I think you're right, we could come up with a matrix that does both at once. Could you also apply those transformations one by one to accomplish the result?
Yeah.
What would that entail in terms of the algebra? What would you be doing with the matrices? Yeah, you would just be multiplying matrices. You have 2 matrices you'd be multiplying. Okay, that's interesting to me. The reason I say that's interesting is because the first thing you said is we're composing 2 functions, right? A reflection and then a dilation or something like that. So for this kind of function, this linear transformation, a composition amounts to matrix multiplication. How do you compose 2 linear transformations? You multiply their matrices, right? Matrix multiplication is the function, right? It applies some geometric transformation. So if composition can happen by matrix multiplication, how do you undo
Matrix division.
How do you undo a transformation that we discussed today?
Like multiplying by the inverse.
Multiply by the inverse, right? Every transformation we talked about today can be undone using the inverse of the matrix to undo it. And then talk to me now about what happens if your matrix doesn't have an inverse. Is it possible that you can do a linear transformation
No.
that can't be undone? Yeah. For example, if your matrix is collapsed down to 0 area, then you don't know where it came from, right? Well, we'll say more about that tomorrow.
Wait, Mr. Chase,
The
what's
homework,
the packet?
yeah, the homework is this packet.
Oh, wait, what packet?
Hey, he was gonna give it to us anyway, guys.
I would have made you print it out.
And you don't want to print it out.
Oh yeah, do you waste more paper than you need? Hey, do you want to give it No,
Did you guys get this over here?
Wait,
Yeah.
How would you describe it? Like in what? Like in why?
Oh, you can just say counterclockwise. Wait, is that you? Yeah. Yeah, you can say counterclockwise. Were you No, we're going to do it till Monday. But we're going to start the new unit. Let's go now. We're going to start the new unit on Thursday, Friday. So you're going to need to...
I'm here.
Oh, you are here.
Yeah, I just didn't know.
There are all these people who've been